With each successive spring, as the poets like to say, we'll find that once again the bird is on the wing. But those warm winds that gently waft our winged wanderers are the same ones that bring the dark, ominous forms of nature's powerhouses over the horizon. The respect we hold for these brutes we have learned from years of bad, sometimes sad experience. Today, every fledgling knows that beneath this exterior of fluff lies a seething mass of turbulence, rain, or hail that is well worth avoiding. Frequently, the effects of this turbulence reach a little further, and with a bit more strength than we may anticipate. And we could have our cabins turned into something out of a slapstick movie, or, more seriously, we might wind up with some very critical injuries to passengers and stewardesses. We have no desire to see anyone hurt, and we do not wish to involve the company in any lawsuits regarding personal injury. With the thunderstorm season now upon us, a brief review of radar and thunderstorm avoidance techniques might prove useful for the months ahead. Over the past several years, we've gathered considerable experience with airborne radar. We've come to regard it as a valuable tool to help us avoid the turbulence and hail associated with thunderstorm activity, and to help us continue our flights safely and comfortably at optimum cruise levels through thunderstorm areas. Let's go over a few basic facts about this tool. We know that radar can't actually detect turbulence. It can only detect precipitation, and while one is generally associated with the other, it does not necessarily follow that a storm cell showing little precipitation will also have little turbulence. We also know that wet precipitation returns a stronger radar echo than the dry ice crystals of snow or hail. So, we cannot conclude that weak displays on our scopes always indicate passable areas. The point is that radar is not primarily a tool for storm penetration, but, as we've stated previously, for avoidance. Certainly, if feasible, the most desired action when thunderstorms are encountered is a complete detour of the storm area. When this is not practicable, we can use radar to unmask the individual storm cells ahead, stripping away their fluff, so to speak, to analyze their interiors. Once we've read the echoes of a cell, we can apply recommended avoidance procedures to pick out the safest and most comfortable corridors leading through the storm area. It's important for one pilot to fly the airplane and monitor, while the other reads the scope and calls out vectors. Some hypothetical examples of thunderstorm cells and their radar scope displays might be helpful here. So, let's suppose we're cruising at 37,000 feet, and we have these two giants ahead of us among a long line of storms separating us from our destination. We'll assume that a detour is impractical. On the radar scope, using the 150-mile range, Storm A to the left returns a fairly well-defined echo, an indication of a mature storm cell that should be suspected of possible heavy turbulence. At this range, Storm B returns only faint traces of an echo. Right now would be a good time to check the 1.3 G Buffett boundary chart to see if our aircraft is at a habitable altitude for turbulence penetration at its existing weight. Once assured that we are, attention can be returned to monitoring the radar. At about 50 miles from the storm, we'll put the seatbelt sign on and switch the scope to the 50-mile range. Reducing our gain control an eighth turn from optimum setting, we see no appreciable change in the strong echo of Storm A. The weak echo of Storm B almost disappears. We reposition the gain and then study the storms on the contour circuit. Storm A shows a rather large, thin-skinned core, confirming it as having the steep rainfall gradient characteristic of maximum turbulence. Storm B might be an area of light to moderate turbulence. Moving in closer, we note some projections forming on the near edge of Storm A. These changes of shape command much attention, since their scalloped edges signal the presence of hail. Watching their possible growth to the pointed or hooked fingers that identify the classic hail patterns may be fascinating on the scope, but any pilot who has ever seen them in person stood a good chance of coming back with an airplane looking like this. Whether they're like bullets or baseballs in size, it doesn't take more than 15 or 20 seconds for hail to do its damage. An anvil head overhang also bears watching. Some of these formations have been known to spit hail shafts out of their tops that strike without warning. respectful avoidance is the best action. As far as avoiding any part of a thunderstorm is concerned, we have a standard yardstick set up in accordance with radar echoes received. For strong echoes, that is, for areas of steep rainfall gradients, apply this rule. Up to 20,000 feet, avoid strong echoes by 10 miles. Increase that distance to 15 miles at 25,000 feet and to 20 miles at 30,000 feet. For other echoes, up to 20,000 feet, avoid them by at least 5 miles. Above 20,000, avoid them by at least 10 miles. Below 20,000 feet, echoes showing areas of weak rainfall may be flown near or through if you deem it to be the best procedure. Let's add here that vertical separation over any echo should be a minimum of 5,000 feet. Now we'll use our yardstick to get past those two hypothetical storms we were up against. At our altitude of 37,000 feet, Storm A and its hail should be avoided by at least 20 miles. Storm B can be safely passed by about 10 miles. Maintaining our present course, we can make this one with ease. Still using the 50-mile range, we'll fly the 10-mile circle past Storm B and clear Storm A by over 20 miles. If you prefer the 20-mile range for avoidance, be sure to switch frequently to the 50-mile range to keep tabs on the full extent of a storm area. It'll help locate distant traps not revealed by the shorter range and go a long way toward keeping you out of trouble. Now, as effective as the use of radar is, it is still only a part of the sound airmanship practices included in our thunderstorm policy. Safety and passenger comfort must be considered first, and so it is the policy of the company to suspend operations over a route or through an area when necessary to avoid subjecting passengers and equipment to any severe conditions generated by thunderstorms. When thunderstorms are encountered en route, the policy stemming from long experience dictates that we maintain VFR and a substantial separation from clouds if possible, that we use all available radar facilities, airborne and ground, to avoid storms, that if a storm cannot be avoided entirely, we should establish the recommended airspeed and provide for the recommended buffered boundary margins for turbulence penetration. Carefully follow all turbulence flying procedures with respect to attitude control, flight instrument scanning, stabilizer trim and autopilot usage as prescribed in our operating manual. And if unacceptable conditions cannot be avoided, the flight should be turned back or landed to wait out the storm. Frequent experience with injuries, too many of them to our stewardesses, points out the extreme importance of being on top of the situation. We want to spot areas of probable turbulence sufficiently ahead of time so that we can get passengers and stewardesses securely under seat belts before the going gets rough. Be sure they are advised on what to expect. And finally, make it a point to keep other pilots and appropriate dispatch officers informed on the location and intensity of any storms or turbulence you find that had not been made known to you. Each new season brings its own peculiarities to the job of flying. The thunderstorm season is obviously no exception. But when we combine good judgment with established procedures and the modern tools of the trade, the inevitable result is a safe, comfortable operation.